Hi, I'm Mrs McTaggart and welcome to this video on prime numbers and decomposition. The lesson intentions today are to be able to identify what a prime number is and list all the prime numbers from 1 to 100 using a famous mathematician's 7 method, and to be able to write a given number as a product of primes using prime decomposition. So before we proceed, you should be familiar with your times tables, and it would be really helpful if you've already seen a video on factors. Okay, so what I've got in front of me here on my computer screen is I've got a prime number detector, and this magnifying glass only lets us see prime numbers. So let's have a wee look, okay? So bear with me. So 8 not prime, 19 prime, 2 is prime, 17 is prime, 5 is, but 39 isn't, 15 isn't, 29 is, 13 is, and the number 1 isn't, and neither is the number 57. So let's have a wee look and think about what these numbers all have in common. So I'm going to circle the ones that it said was prime and the ones that weren't on the next slide. So let's just recap what we did there in that video. So I'm going to circle all the ones that we said were prime. So 19, 17, 2, 5, 29 and 13 were all prime numbers. Now, what do they all have in common? Let's have a wee think. Now, with the exception of the number 2, they're all odd. And a wee clue would be the fact that we've mentioned the word factors already. When you were asked to find factors of a number, were you asked to find factors of any of these numbers here? Probably not, because let's have a look at how many factors I've got. Numbers that multiply to 19 are 19 times 1. Numbers that multiply to 17 are 17 times 1. Numbers that multiply to 5 are 5 times 1. 13 is 13 times 1. 29 is 29 times 1. And 2 is just 2 times 1. What do you notice about all of them? Can you think? The factors, there's only 2 factors for each of these numbers, and it's itself and the number 1 each time. Now the reason number 8 wasn't prime is because it divided by 1, 8, 2 and 4. It had lots of factors. So did 39, it divided by 1, 3, 13 and 39. 57, you might not be aware, but that actually divides by 3, okay? Because 60 divided by 3 would be 20, so that's 19. So all these other numbers have lots of factors, except this one here, the number 1. Okay, the number 1 quite often people will tell us is prime, but if you write down the factors of 1, to get the number 1, that is a product of 1 times 1. That isn't 2 different factors, is it? That is both a repeated factor again. So it only has 1 factor. So all these ones that are circled are called prime numbers. So here is your definition. A prime number is a number that divides only by itself and 1. And I can't stress that number 1. And number 2 is special because number 2 is the only even prime number. So number 2 is special as it's the only even prime number. So basically, other than the number 2, we can rule out all even numbers as being prime, and we can just focus on our odd ones, because any even number divides by 2 and something else, therefore it's going to have more than just 2 factors. So let's have a wee look. Which of these following numbers are prime? So by listing the factors, you can decide which are not prime. 27 divides by 1 and 27, and 3 and 9, so it's not prime. Number 51 divides by 1 and 51. Does it divide by anything else? It's certainly not in any of our regular times tables. But what's worth checking is, you then try dividing it by other prime numbers. 3 and 7 are the ones to watch out for. It clearly doesn't divide by 7, but I'm going to check. Does it divide by 3? 3 into 5 goes once. Oops, I've not even written the number in. 3 into 5 goes once, carry the 2. 3 into 21 is 7, so actually it divides by 3 and 17, so that's not prime either. 49 divides by 1 and 49. but it's also 7 times 7. So it's got 3 factors, so it's not prime. What about 91? Certainly not in any of my times tables. It doesn't divide by 3, because 90 divides by 3. Does it divide by 91? Sorry, does it divide by any other prime numbers? Let's try 7. 7 into 91. 7 into 9 goes once. Carry the 2. 7 into 21 is 3. So it's not prime either. So none of these are prime numbers. Let me throw one more in. What about the number 119? Does it divide by anything? It's certainly not in any of the times tables we know very easily. We're going to check, does it divide by 3? Well, 120 would divide by 3, so it doesn't divide by 3. Does it divide by 7? Let's have a wee look. 7 into 119 is 1, carry the 4. Oh God, it does divide by 7. I keep picking numbers that aren't prime, but this is a way you would check. Does that make sense? So if you're not sure, try dividing by 3, try dividing by 7, try dividing by maybe 11, other prime numbers. So at the end of the day, none of those were prime. So my next question is sometimes asked this in tests. Write down all the prime numbers between 80 and 90. So basically what you do here is you write down all the odd numbers. I'm going to write them down, but you would probably just go through them in your head. So we write down all the odd numbers because we've already ruled out the evens. Right, 81 definitely isn't prime because it's 9 times 9. 85 definitely isn't because it ends in a 5, so it divides by 5. Let's have a look at these other ones. 83 doesn't divide by 3. It doesn't divide by 7. It doesn't divide by 11. Therefore, I reckon it's prime. So 83 is a prime number. 87, well, I know straight off that's not prime because that's 3 away from 90. So if you do your 3 times table backwards from 90, 90, 87, that divides by 3, so it's not prime. And then 89, not any numbers in your timetables. Doesn't divide by 3 because 90 does. Doesn't divide by 7 because 84 does. Doesn't divide by 11 because that would be 88. So there are your 2 prime numbers. So prime numbers between 80 and 90 are 83 and 87. And if you were doing that in a wee test, that's the same kind of process you would do. Question 3. So let's write down what the first 15 prime numbers are. So we already said number 1 wasn't prime because it doesn't have 2 different factors. And 2 was the very first prime number and it was the only even one. Then we would have 3 because that only divides by 3 and 1. 5 only divides by 5 and 1. 7 only divides by 7 and 1. 9? Does 9 divide by anything else? That's right, 9 divides by 3, so it's not prime. 11, definitely not in any of your times tables. What else? What about 13? Not in any of our times tables. 15's in the 5 times table. 17. What else? 19. Next odd number would be 21. Is that prime? Is that in any of your times tables? That's right, 21's in the 3 and 7 times table, so we can rule it out. What about 23? Definitely not in any of our tables. 25 is in the 5 times table. 27 is in your 3 and 9 times table, so that brings us to 29. 29 is definitely prime. So that's us got the first 10. Now we're going to go through our 30s. So 31 definitely isn't prime. 33, well, it divides by 3. It's 3 times 11, so not 33. 35 ends in a 5. 37, definitely prime. What about 39? That's your 3 times table again. Which brings us to 41. 41 is prime. Doesn't divide by anything else. Doesn't divide by 3, 7 or 11. What about 43? Again, doesn't divide by anything. What about 45 is in the 5 times table. 47, does it divide by 3? It doesn't. 48 would, so 47. So there are our first 15 prime numbers, and you'll see we're already halfway through the numbers 1 to 100. However, this gentleman here, I'm not even going to try and say his name, he came up with what was called a mathematical sieve. Now a sieve, you've hopefully seen a sieve in your kitchen. It's a way to like separate things, so you can like sieve out the flour from the clumps and stuff like that, or you can sieve out rocks from sand. So mathematically it's going to sieve out all our prime numbers. So this allowed you to sift out all the non-primes, okay, on a times table at a time, thus leaving only the prime numbers. And there are 25 altogether. Now we've already got the first 15, so it means we've only got 10 to go. So let's have a look at what he did. So here are your numbers 1 to 100. Now straight off, I can eliminate any even number. So let me do that very quickly. So there I've sifted off all my even numbers, but remember I left that number 2. Now we already said that the number 1 definitely wasn't prime, so I'm going to score that in. Next we're going to get rid of our 5 times table, so let's score out anything that ends in a 5. And obviously I left the number 5 because we already said it was prime. So that's us done our 5 times table. Then we can go through and we will do our 3 times table. So our 3 times table. So 3 is okay, but 9 isn't. So you've got 3, 6, 9, 12, 15, 18, 21 is in the 3 times table. 27 is in the 3 times table. We know 33 is in the 3 times table. And 39. Now at this point we'll have to just keep adding on 3. So 39 add 3 is 42, 45, 48, 51. So 51 gets to go. Add on 3 is 54, then 57. And then that gives us to 60. Then we can go 63, 66, 69. So bye-bye 69, 72, 75, 78, 81. Okay, 81 add 3 would be 84, which is already gone. 84 add 3 would be 87. And then that brings us to 90. And then we can rule out 93 and 99. Okay, so we're getting closer. So we've done the 3 times table. We've done the 5 times table. We're going to just do the 7 times table now. Now most of them have already gone. So we had 7, 14, 21, 28, 35, 49. So 49 is in the 7 times table. Then we had 49, 56, 63 already gone. 70's gone, 77. That's also in your 11 times table. So 77 has gone. And then that gives you 84 and it gives you, 91. We already did that one in an earlier question. So that leaves us with 25 numbers. So there you go. There are all our prime numbers between 1 and 100. And really that's the only kind of activities we'll ask you to do with doing prime numbers. So the next thing we look at with prime numbers is we look at this thing called prime decomposition, right? It sounds scary, but it's not. Think of the word decomposition. Have you heard that word before? What about the word decompose? Decompose is when, think of your compost patch. Things decompose, and then it means they break down. Now, the same thing happens in maths. We break down a number by splitting it into a series of factors. So we're breaking it down into another way of writing it. And the way we write it is we want to write it as a product, which is a fancy word for times, of all prime numbers. So here is an example of what's called a factor tree. So we started with the number 20 and we split that into 2 factors, 4 and 5. Now there was other options. I could have used 2 and 10. I wouldn't have used 20 and 1 because that wouldn't have really got me anywhere. But I could have used 2 and 10, and I'll show you that this works just the same both ways. So we split it into 4 and 5. That 5 is now a prime number, so we circle it. But 4 isn't prime, so you split up the 4 again. 4 is 2 times 2, which are then prime numbers. And then that's you done. And then what you do at the end is you write 20 equals, and you put all the circles into order. So that is 2 times 2 times 5. That is 20 written as a product of prime numbers. And if you want to check, 2 times 2 is 4, 4 times 5 is 20. Now another way to write this is 2 times 2, you should hopefully know, is 2 squared times 5. So some of the answers have it written like that instead of all out the long way. Now just to prove that this could work using the other pair of numbers, so we could have used 2 and 10. 2 was in prime, so we stop there. 5 can then be split up into 2 times 5. 2 is in prime, 5 is in prime. we still end up with 2 times 2 times 5. So just to prove to you that if you were doing this in class, the way you did it wouldn't always be the same as the way your neighbour did it. Just see, it depends what times table jumps out at you first. So we're going to try a couple of these ourselves now. So we have to write 63 as a product of prime numbers. So we have to start with the number 63. And we have to think, right, what numbers go into 63? Now I'm hoping either your 3 or your 9 times table jumps out at you. I'm spotting a 9 and a 7. 9 times 7 is 63, so we do 9 times 7. Now 7 is prime, so we stop there. But 9 isn't. 9 can then be written as 3 times 3. Now 3 and 3 are now prime numbers, so we are done. That's us at the end of our factor tree. So then you say, well, 63 is the same as 3 times 3 times 7. And remember, you could write that as 3 squared times 7. And you just put them in order from small to big. That's you done prime decomposition. And it's not that bad. So question 5, we're going to do a bigger number. Let's start with 100. So again, you've got loads of options. And the pair that I'm going to start with might not be the pair that jump out at you. We can use so many things. We could use 25 and 4. We can use 5 and 20. We can use 50 and 2. We could use 10 and 10. I'm going to go with 10 and 10. And that might give me a nice wee symmetrical tree. So 10 and 10. Neither of them are prime, but 10 can be written as 2 times 5, which are both prime. And the other 10 can be written as 2 times 5 again. So what we've got, if we put these into order, 100 is the same as 2 times 2 times 5 times 5. And I'm going to write that as 2 squared times 5 squared. And let's double check. 2 squared is 4. 5 squared is 25. 4 times 25 is 100. Let's get one more. A big number, 288. So 288. Can you spot anything that goes into 288? There's quite a lot of numbers. If you're struggling, the easiest thing to do is start with a 2 and half it. So that would be 2 and 144. And I don't know why I'm circling them, because 144 isn't prime, but 2 was. Right, what goes into 144? If in doubt, why not use 2 again? So that would be 2, which is prime. And half of 144 is 72. Numbers that go into 72. What about 9 and 8? Neither of them are prime. 9 would then be 3 and 3, both prime. 8 would be 2 and 4. Oh my goodness. The 2 is prime, but the 4 isn't. And then the 4 would be 2 times 2. Now I reckon I could have got a lot there quicker. See if I'd just spotted that 144 was 12 times 12. That might have been a quicker tree to go. But the point is, I just wanted to show you that you can keep going. And it might be a series of 2s. So let's see how many 2s we've got here. So we've got 288 equals. So we've got 1, 2, 3, 4, 5 2s. So I'm going to go straight to 2 to the power 5 because there's 5 of them. And then we've got 2 3s, which is 3 squared. And that's that one there. So that's how you would write 288. So this is the point where you're going to try some of this for yourself. So this is just practicing your prime decomposition. You have got 8 there to try for yourselves, okay? Some might take you a wee while, some might not. And then there's a wee challenge. So the last 3 are a wee bit trickier because they're such big numbers. So pause, give them a wee try, unpause and check your answers. So there's your answers there. And notice I started off writing them with the option of ways to do them. But then I just started writing them as a quicker way because I had so many 2s and 3s and that going on. So hopefully you got on okay with them, and especially maybe with the challenge ones. So what have we learned today? We've learned the definition of a prime number. It's a number with only 2 factors, 1 and itself. Okay, and the special thing was, number 2 was the first prime number and it was the only even one, right? So if you take anything away today, please try and remember 1 is not prime. Biggest classic mistake made in the classroom. We've learned how to decide if a number is a prime. You start going through all your times tables, and remember I said focus on try the 3, try the 7, try the 11. So try dividing it by other prime numbers or times tables you might know. And we've learned how to draw a factor tree and how to do prime decomposition. and write it as a product of primes. Now remember, a question won't say the question won't say use a factor tree or solve this using prime decomposition. It will use that phrase there and ask you to write as a product of primes. Thanks very much for watching.